Welcome. We have been looking at the phase field equation. In fact, in the last lecture we derived the phase field equation. In this lecture we are going to continue looking at the phase field equation, its solution and solving it using octave, and how the solution looks under different scenarios and so on and so forth. So, in this lecture and the next lecture we are going to remind ourselves of some of the things that we did with respect to the diffusion equation. So, there is some amount of repetition, but to understand phase field modeling better, it is always better to compare it with the diffusion equation and its solution, which we know well. So, with respect to it, then the discussion becomes easier. So, I am going to repeat some parts of what I did earlier as part of this lecture, but now we are looking at it from the point of view of comparing and contrasting with the phase field equation. So, let us write down the two equations that we are going to use extensively today. First is the diffusion equation. So, of course, that is written as dou C by dou T is equal to m by n v f double prime del squared C by del x squared. This is 1D diffusion equation. The difference is that usually this quantity is called diffusivity D, but now we are writing the diffusion equation in terms of mobility and free energy per atom and its curvature, and Nv is the total number of atoms in the given volume. So, it is typically Avogadro's number. So, this is what we are using, and we also derived the phase field equation. And the phase field equation was like this: dou C by dou T is equal to m by n v. This is the reason why I wrote the other equation also like this, because it is easier then to compare with the phase field equation. Del squared C by del x squared minus 2 kappa del power 4 C by del x power 4. This is the 1D Cahn-Hilliard equation. It is clear how these two equations came about. This equation came about because we said that free energy is a function of composition, and we said that the composition evolution should be in such a way as to minimize free energy. That implies equalization of chemical potential everywhere. And because free energy is a function, then regular calculus you can do and try to minimize the free energy, and the rate is determined by the diffusion. So, this is how we got this. So, we basically had a constitutive law which said that the flux of atoms is proportional to chemical potential gradients, and the constant of proportionality was called mobility, and it had a negative sign because it said that chemical potential gradients are getting evened out. And then we used the mass conservation and we ended up with the 1D diffusion equation. Now, when we did this, we said that the free energy is not just a function of composition, but it is also a function of composition gradients. The reason for introducing the gradients was that if you did not introduce the gradients, you got results which were not consistent. In other words, if you looked at the spinodal region, which from a regular solution like model we know is because AB bonds are not preferred, and under such scenario, if you try to solve the usual diffusion equation, that is the 1D diffusion equation I have written here, then because the diffusivity becomes a negative, the solution is such that it ends up producing a solution which is equivalent to ordering. And in the case of ordering, it is the AB bonds which are preferred, but we started with a system which is supposed to prefer AB bonds, but the continuum equation gave a solution in which it says that it prefers instead of preferring AA BB bonds, it prefers only AB bonds. So, that to avoid that contradiction, we realized that the mistake we did when we wrote this is to assume that free energy is just a function of composition, because any interface that forms between two phases is a region where there is a compositional gradient, the composition changes from one value to another. So, that gradient actually contributes to the free energy, that is the interfacial free energy. The excess free energy associated with the interface is the interfacial energy, and we did not incorporate that into the calculation, and that is the reason why, because we neglected that contribution, we ended up with this contradictory situation. So, we realized that if you can incorporate the information about the composition gradients, which basically talks about the interfaces in the system and the excess energy associated with them, their contribution to the free energy, if it is accounted for, then you will get the right solution. So, that was the argument. So, we took a free energy, we wrote a free energy functional by assuming that the free energy is not just a function of composition, but its gradients and curvature and so on. So, we Taylor expanded that, and we used some symmetry arguments, intrinsic symmetry arguments as well as underlying crystalline symmetry arguments, and showed that if you restrict your Taylor series expansion to the first term, the gradient term anyway goes to 0. That can be argued in two ways, either by assuming that underlying crystalline symmetry demands inversion symmetry, or by saying that we are going to be looking at systems where there is going to be a minima or maxima. In such cases, the first derivative term cannot exist because that is a necessary condition. So, either way, that first term is not there. So, the things that survive the first term after the F0 term in the Taylor series expansion is a second rank term. So, second rank term in gradient and second rank term in curvature. So, if we restrict ourselves to that term, and odd rank tensors are all 0 if you are assuming inversion symmetry. So, third rank is not the next term, fourth rank is the next term. But if suppose we say that the composition gradients we are looking at are such that the free energy can be approximated up to this and higher order terms are negligible, then you get to a free energy functional. That free energy functional was just a function of C plus some constant times gradient squared, provided we are looking at isotropic or cubic systems. So, we assume that we are going to look at isotropic or cubic systems. So, in such systems all second rank tensors are isotropic, and that obeys Neumann principle, because cubic symmetry it has to be minimum cubic symmetry, it can be more symmetric than that. So, isotropy is more than cubic. So, that is okay. So, we assume that that is a constant, and we also used the integration by parts to reduce all the gradient and curvature terms to one single gradient term multiplied by a constant. So, that constant, which we called as kappa, which is here, is known as the gradient energy coefficient. And so, and when we wrote it, and if you change it in terms of derivatives of concentration profile with respect to position, then this is what you end up with. And this is known as a Cahn-Hilliard equation. This is the one dimensional version that I have written here. So, with respect to the diffusion equation, you can see that it is just a modified diffusion equation, in that it has some higher order terms. Now, this higher order term, which incorporates the gradient energy coefficient, is going to take into account the interfacial contributions, and this is what is going to make sure that when you have all these concentration gradients that are growing, some concentration profiles, suppose if they are varying too much, then this term is going to kill them. So, the lower wavelength limit of the wavelengths that can grow is going to be determined by this second term. So, in this way is how this equation is going to solve the problem that we found while using this equation. Remember, when we were using this equation, we found two things. One was that if you considered the regular the diffusion equation, dou C by dou T was d del squared C by del x squared. So, when we were looking at the spinodal region, so if you had a free energy like that, and then there was this region which was supposed to undergo phase separation using spinodal decomposition. In that region, when you look at, there were two things that were happening. One was that this diffusivity was suddenly becoming negative. Now, this term now explains why that becomes negative, because the f double prime sign changes, it becomes negative. So, that is the reason why the diffusivity becomes negative. So, that is one part. But that alone was not sufficient, because even if you took this to be negative and you tried to solve, you found a contradiction, namely that you were looking at a spinodal region, but you get a solution which says that the system is ordered. So, to avoid that problem is why we had to go for the free energy functional approach. So, classical calculus is no longer valid for us. So, we did the variational calculus and we arrived at this equation, which is the Euler-Lagrange equation, which gave the chemical potential. So, we use the same constitutive law, namely that flux is proportional to chemical potential gradient, and then we use the mass conservation law and we ended up with the Cahn-Hilliard equation. So, now what I want to do is that, so when we solved the diffusion equation, we assumed that the non-dimensionalization is done, so that the diffusivity can be assumed to be 1. In the case of diffusion equation, the non-dimensionalization just involved position and time, and we could non-dimensionalize. But in this case, in addition to position and time, that is the length scale and time scale, there is also an energy scale associated with the interfacial energy that comes from here. So, the non-dimensionalization should also involve energy. So, we will do that as a tutorial, how to non-dimensionalize this equation. For all practical purposes, we are going to assume m by nv to be 1 and kappa to be 1. So, when we solve numerically today, I am going to assume that this quantity is 1 and this quantity is 1. In fact, this quantity multiplied by this second derivative by nv, I am going to assume as 1, because strictly speaking f double prime is a function of composition. So, you have to actually incorporate that effect also, but what we are going to do is that m f double prime by nv, and we are going to just call that as some d tilde, and we are going to assume that that d tilde is non-dimensionalized to be 1. So, that is one thing. So, non-dimensionalization, we will do it separately, and we are going to assume that non-dimensionalization is already done for today's lecture, for this lecture. The second thing is, of course, that we said that the curvature of the free energy is needed, but what is the free energy expression is something that we have not written down. Okay. Now, we are going to use a very simplified free energy expression. Okay. So, you know that, for example, if you used a regular solution model, your free energy expression had terms like, I mean the delta f had terms like omega x into 1 minus x plus RT x log x plus 1 minus x log 1 minus x. So, if you see, these are logarithmic terms and they are very bad for numerical implementation. So, what we are going to do for the purposes of this lecture is to assume that the f term that we are going to assume. So, remember, I mean we assumed a free energy functional which was like this. So, some f0 plus kappa del c squared integrated over dv, this was our functional. So, we want to have an expression for this f naught. So, all that I am going to demand is that this f naught, see in the regular solution this thing, if you looked at the f naught, it will be a function that is like that. Okay. So, what I am going to say is that I am going to approximate this, or I am going to replace this by a very simple minded function, and that function is as follows. So, I am going to assume my f0 to be nothing but a c squared into 1 minus c whole square. Now, this is a fourth order polynomial, and so if you try to minimize it, you will get 3 extrema points. They are at c equal to 0, c equal to 0.5, c is equal to 1. In other words, what we are doing is that we are doing some transformations on such a curve by bringing the minima. So, we are going to push the maxima to be at the center. So, that will be true even in regular solution model, because it is symmetric about the 0.5, but when you add this G A G B, so these curves get shifted. So what we are going to do is that we are going to put the maxima in the middle, but the minima need not be at 0 and 1, the minima is actually away from 0 and 1 in this case, but we are going to push them to go to 0. So, I am going to make one minima go to 0 and I am going to make another minima go to 1, and I am going to assume that the f value at these 2 points is going to be the same. So, that is what is achieved here. So, taking a regular solution free energy, how do you arrive at such a free energy? So, what are the transformations you have to do on such a function to achieve this is again another tutorial. So, we will be doing 2 tutorials, one is to do non-dimensionalization, the other is to show that you can take a free energy expression which is like the regular solution expression and it can be transformed mathematically into a very simple function like what I have shown. So, because it is a 4th order polynomial, its first derivative will have 3 roots and these are going to be the roots, and it is going to have minima here and here, and it is going to have a maxima here. Now, A is a constant, and what does A represent is something that we want to do, and that we will do next by plotting this function for different A values and trying to understand what the A value means. Okay. So, we will do that using octave. So, that is what we will do in the next part. Thank you.